Okay, good. Welcome, everybody. It's a great pleasure to have Malcolm Perry joining us today. I'm guessing all the way from Cambridge. I'm not quite sure whether Malcolm's in Cambridge or London.
I'm in Histon, which is about 4 miles from the centre of Cambridge.
Okay.
And the reason I'm at home doing this is because my computer in Damped has neither a microphone nor a camera.
Great. Well, in any event, it's wonderful to have Malcolm joining us. It's only a pity that he's joining us virtually. Malcolm's been to Cape Town before, and it was wonderful hosting him then and touring the wine farms. And
hello, Malcolm.
Hello. That must be Amanda, but I can't see you.
I'm here.
That's Amanda with our new baby.
Oh, fantastic! I can't see a new baby either.
It's okay.
There you go.
I think he's seen the screen.
Anyway, so great. Malcolm will be talking to us about a rather bleak topic, and this is the fact that there's no future inside black holes.
Oh well, it's not a bleak topic, as you will see. It's a very promising topic. Before I go any further, I must say that it's a great pleasure to be virtually in Cape Town, although reality would be much better, especially because you are able to grow wine and Britain is not, despite propaganda by the government to the contrary. As in many cases, they've got it all wrong. So what I wanted to basically describe to you was a possible new way of looking at the information paradox of black holes, which, as Jeff just said, sounds bleak, but actually is no bleaker than it was before, as we will see. So let's start from the very beginning. The general picture of black hole evaporation is summarized in this kind of Penrose diagram. As you can see, you start off in some initial state on a space-like surface sigma I. You imagine that you have collapsing matter, and in classical or even semi-classical quantum gravity, you end up with a space-time singularity hidden behind a horizon. And then you hope that on the surface sigma F, there will be some kind of matter corresponding to the Hawking radiation, which contains all of the quantum mechanical information on the surface sigma I. That is to say that there ought to be a unitary map between sigma I and sigma F, and if there isn't, you'll conclude that quantum mechanics breaks down. Since there is no evidence that quantum mechanics breaks down, it's a good idea to see if you could understand how and what would happen, what is needed for quantum mechanics to be fine. You might protest that the singularity that I have drawn is a space-like singularity. This picture looks like an evaporating Schwarzschild black hole, and the collapse looks like the kind of thing that you would have encountered in Oppenheimer Volkoff type of picture, because the singularity is a space-like singularity, and that's not what you see in the Kerr space-time. In the Kerr space-time, the horizon would lead to another region where there would be a Cauchy horizon, behind which there will be a time-like singularity. But you probably shouldn't believe that picture for the simple reason that the inner horizon is an unstable place. Perturbations there grow up, and it is widely believed that it will be replaced by either a space-like singularity or a singularity that is space-like in parts and null in parts. So the picture that you see here is generally thought to be a generic kind of picture that you would expect in gravitational collapse and when the black hole evaporates completely. So here we have a picture, well, it illustrates Oppenheimer-Snyder collapse. It's taken to be generic, and the unitary evolution between sigma I and sigma f seems impossible for the very simple reason that at the singularity, stuff just is going to go down to the singularity and disappear off the space-time. Classically, so here's problem one. Classically, anything that passes through the event horizon is going to reach the singularity. And since the singularity is the boundary of space-time, anything arriving there has left the space-time. And surely if you want to have a unitary map between sigma I and sigma f, that is not something that you want to have happen. If you try to do something quantum mechanically, what you'll discover is that in the linearized theory, for the Schwarzschild metric, wave functions do not vanish at the singularity, and indeed some of them will blow up. The probability current there is non-zero, and so stuff simply falls off the edge of space-time in a quantum mechanical picture too. So that's our first problem. There is a second problem, which is really posed by the idea that black holes have an entropy. We all know from the treatment of Bekenstein and of Hawking that the entropy of a black hole is supposed to be equal to a quarter of the area of the event horizon. Let's see what that actually means in practice for an evaporating black hole. So here you have some Hawking radiation. The Hawking radiation is supposed to be more or less thermal, so it will contain some kind of entropy. But you want eventually for the black hole to evaporate completely and all of the information be contained somehow in the Hawking radiation. So let's ask ourselves what happens if there's a little bit of extra Hawking radiation due to the pair production of an X and an X prime, whatever those may be, some bits of Hawking radiation. They will add to the Hawking radiation that you had in the past and produce Hawking radiation up here with some combined entropy SRX. So you start off with entropy SR, and you end up with entropy from this combined state SRX. Let's ask ourselves what happened to the black hole. Well, it starts off with some entropy SH. You're going to add the particle X bar to this. You'll end up with entropy SHX bar. And if you think that the black hole is going to decrease in size, SXHX bar is going to be less than SH. The other thing that you know is that you have pair production here. S of X bar had better be equal to 0 because they are fully entangled pair. And so you have this result here. So far that's all fine. Since you want the black hole to evaporate and retrieve information, SRX had better be less than SR. So the entropy here is less than the entropy here. And again, the entropy here is less than the entropy here. What does that mean? Well, if you think about it, what you have done is to construct a situation that is essentially contradictory. The entropy of the pair SX bar XX bar is equal to 0, but there is no reason why S of X and S of X bar should be equal to 0. They're just equal to each other because they are fully entangled. We know that SH is bigger than S of HX bar because Hawking radiation decreases the entropy of the hole. You know that SR is greater than SRX because, again, Hawking radiation has got to decrease its entropy if you're going to have a unitary map. Then there's a theorem due to, I guess, essentially Elliott-Lieb, which tells you that there is strong additivity of entropy. That is, if you take any three entangled systems, R, X, and X bar in this case, then if the usual rules of quantum mechanics and statistical mechanics hold, then there's an inequality. It says that S of Rx plus S of X bar has got to be greater than S of R plus S of X bar. We don't know what S of X bar is. We don't know what S of R is, but they are positive. S of X bar is equal to 0. And so that tells you that S of Rx minus S of R minus S of X bar is positive. But for black holes to evaporate without giving rise to a contradiction, S of Rx minus S of R had better be negative. Therefore, there is a contradiction. S of Rx is less than S of R, so that's a contradiction with this inequality. So it must mean that strong additivity of entropy doesn't work, and that means there's something wrong with quantum mechanics inside the black hole, or something wrong with statistical mechanics inside the black hole. And that is problem 2. Now, how are we going to approach this kind of problem? Well, the basic idea is that we need to understand how non-equilibrium systems evolve in gravity, because we're dealing with a system that is way out of equilibrium. So you need to generalize the path integral for gravity. So leaving out all the details of this, typically what one does is you think about how you're going to evolve from some initial state to some final state, typically at time ti, initially as going to time tf, and that's given by integrating over, well, integrating e to the I action over all 4 geometries that interpolate between spatial geometries gamma I and gamma f. And one way of doing that is just to consider the path integral. Of course, you could object and say, well, it's not very well defined because the problem is that in gravity, this theory is not going to be renormalizable if it's the Einstein theory, and we don't know of any other one that works well under all circumstances. But let's leave aside that issue for the moment. Perhaps at the very end, I'll tell you my view on the subject of renormalizability. You could replace this by string theory, and it wouldn't make much difference if you thought that string theory was really a theory of space-time. And then you wouldn't be faced with the problems of infinitives, but you'd still be faced with the problems that we've just discussed. So suppose that you, that's what I wanted to do. Suppose initially you have some density matrix, rho initial. That, of course, will involve 3 geometries, gamma I and gamma I prime, not necessarily the same. If you wanted to, you could include extra fields along with these spatial geometries, but that's just an irrelevant complication for what's going on here. The basic idea is you just have some density matrix, rho I, instead of just some ordinary geometry. What difference does that make to the path integral? Well, that problem was looked at a long time ago, in the early 1960s, by a group of people, were all working more or less independently. Keldysh in the Soviet Union, Schwinger at Harvard, Kazanov and Baim in Illinois. And they showed that the probability of finding a system in the state gamma f is going to be proportional to a sort of doubled path integral. Here you have the initial density matrix, and then there's a forward path integral where you integrate over all 4 metrics which interpolate between gamma I and gamma f. But then there's an e to the minus I g prime. This is separate 4 metrics which interpolate between the final geometry and the initial conjugate geometry, gamma I prime. And again, you can include other fields in this. So G interpolates between gamma I and gamma F, and G prime interpolates between gamma I prime and gamma F. You might think that that just means that you square the path integral, but that isn't actually what happens. It would be true if you were just dealing with a free theory, but in theories with interactions, and of course gravitation has interactions, these 2 different path integrals are not independent and involve geometries that join the forward direction and the backward direction. That's something which needs further exploration. And again, I will come back to that in a moment.
Sorry, Malcolm, can I ask a question?
Sure.
Can I think about that kind of doubling as something like the replica trick that you would do in disorder systems?
I didn't think so. And the reason is that gamma, you see, the thing that you're integrating over is a geometry. So what you would want to do if you wanted to think about that kind of double copy would be to replace gamma by some kind of gauge field squared. I don't think so, but perhaps it's worth looking at.
So I guess I ask because the words kind of sound like you've got two copies, two sheets, like a double sheeted Riemann surface where you've glued, you know, gamma f on one sheet to
Sure.
gamma f on the other sheet, kind of thing.
What you say sounds precisely right, although I don't think it's the same thing, but I would encourage you to investigate. The most clear statements of what's going on can be found in the Keldysh paper and the Schringer paper. The book of Kadanoff and Bain that explains this is rather obscure. There is a book that is relatively recent by a gentleman called Kamenev, which does explain in fair detail for quantum mechanics how the forward and the backward path fail to be independent, and that's worth looking at. But in terms of double copy, I'm not sure. It doesn't seem right to me, but that may just be a reflection of my ignorance.
Yeah, thanks.
So here's the next problem. One thing that we do know is that the laws of physics are time symmetric. Time symmetry always seems to arise as a result of choosing some kind of boundary condition somewhere. For example, in electrodynamics, or indeed in more or less any field theory, in flat space at any rate, you pick retarded versus advanced solutions, or in the case of quantum field theory, you pick something which is time ordered, or possibly anti-time ordered if you're going along the backwards path. And so by time symmetric, I mean CPT invariant. I don't really mean time reversal invariant because CP is violated. But nevertheless, you don't really have a direction of time. It's not true, for example, in electromagnetism. It's not true in gravitation unless you put it in by hand. The same is true for fermions, even though they're first order equations. In quantum mechanics, you think of time asymmetry as coming from the collapse of the wave function, and the observation reduces something. But the problem with that is that it's not really a quantum mechanical process, and all processes are supposed to be described by quantum mechanics. It is at some level either mysterious, classical, or simply a process that is mystical, and it only really takes place in Niels Bohr brain. So I don't really understand collapse of the wave function. It's sort of a good rule of thumb, but it's not really something which seems to be of fundamental importance. A better way of thinking about things is consistent histories, in which what you do is you regard various things, anything that you can think of really as an event, and events correspond to projections in the Hilbert space. And that seems a more appropriate thing to do. And then you can argue that classicality emerges from these projections. And I'm not going to try to explain that, but merely refer you to the papers of Gell-Mann and Hartle, who have dealt with this problem at great length. Now, one nice thing that, again, dates back to the 1960s, some work of Aharonov, Bergman, and Leibovitz, they proposed a time-symmetric version of quantum mechanics in which one specifies both the initial and final density matrix. That's really just a very simple extension of what Keldysh and Schwinger and Kadanoff and Boehm did. They will tell you the probability of finding a system in the state rho f, given that it is in the state rho I, is proportional to the expression that you can see there. And what you can see is it's very similar to what you had before. There's going to be a forwards directed path integral, which goes between gamma I and gamma f. There's a missing I here, a reversed one, where you go between gamma f prime and gamma I. Again, the four-dimensional metrics will interpolate between these three-dimensional geometries on space-like surfaces. And again, the paths in the forward and backwards direction are not independent of each other. You can get back to the conventional situation of Keldysh and Schwinger, or conventional quantum mechanics, by simply setting the final state density matrix equal to the unit matrix. That gets you back to where you started from. So you could say that that's a boundary condition that you would like to have. But it's not necessarily that case. It might be that rho f, the final state density matrix, is some non-trivial thing. And specifying rho f is usually referred to as post-selection. And various people interested in quantum information have invented experiments where you can actually set rho f equal to something. And these ideas have been verified in the laboratory. There are some papers of Aharonov and his friends in Physics Today, which give reasonable explanations of how that happens. So the question is, could it be that in black hole evaporation, there is a rho f that is somehow a non-trivial rho f and applies boundary conditions at what classically would be called the singularity, which prevents loss of information? So let's turn our attention to trying to see if that's possible. So the way in which I approached this was to think about what happens when you have gravitational collapse to form a realistic singularity. So the way to deal with this, or the only way I know how to deal with it, is in canonical gravity, where we're going to split space-time into space and time in the usual way. So you can write a general metric in this form. Alpha is going to be the lapse. Time is separated out in this way. Gamma is going to be the geometry of space-like surfaces, and of course could give you a shift specified by some vector field beta I. These i's and j's will be raised and lowered with respect to the three-metric gamma. So you've got a lapse and a shift and the usual spatial three-metric. And one nice thing that comes out of this is that alpha and beta, the lapse and the shift, have no momenta conjugate to them, and therefore are pure gauge. You can specify them to be anything you like. So putting them equal to something simple makes life nice. So really the only physical degrees of freedom here are going to be of the three-metric gamma ij. The embedding of gamma ij into the space-time is defined by the second fundamental form, gamma ij of the surface t equals constant. And the second fundamental form can be written in terms of the lapse, the shift, and the spatial metric in this way. It's 1 over 2 alpha, and then the covariant derivative of the shift, symmetrized, minus the time derivative of the three-dimensional spatial geometry. Dot is going to stand for time derivatives of everything we're going to do. And this d here is covariant derivative with respect to the spatial metric gamma ij. Then you find the momentum conjugate to gamma ij is just this thing. It's going to be a tensor density. Momenta always are. And it involves gamma to the half. So it's tensor density in the free space. And then just the second fundamental form and gamma. because we're dealing with a gauge theory, for each degree of freedom which has no momentum conjugate to it, there will be a constraint. There are two types of constraints. There's a diffeomorphism constraint, chi ij, which is just equal to the divergence of the momentum conjugate to the 3 metric, and the Hamiltonian constraint, h, which looks like this object here, which is usually called the DeWitt metric, times pi squared minus gamma to the half 3r. If you were not thinking too rigorously, you would say, oh, this h looks like the kind of Hamiltonian that you find in quantum mechanics. There's a momentum squared, and then there is a potential term, which is just the 3-dimensional Ricci scalar of the metric gamma. If that was the case, then you'd say, ah, this G is a contravariant metric on the space of all 3 metrics, and it is going to look like this expression here. So if you think about each point in space, you'll see that G has got 5 space-like directions and 1 time-like direction. That simply means that if you started to ask yourself, what is the signature of this thing? Well, it would say it was got 5 pluses and 1 minus. If you ask yourself, what does the time-like direction correspond to? Well, it corresponds to conformal transformations of the 3-metric gamma. And then the space orthogonal to that is going to be just the coset space here, SL3R over SO3. So this is something which you would impose at each point in space. So let's go back a little bit. So if you thought this was a bit like the Schrödinger constraint, Schrödinger equation, your Hamiltonian would be basically saying you'd had 0 energy. Now, I cheated a little bit. I didn't worry about the boundary of space here. If you consider spaces which are asymptotically flat, then this thing will have some extra terms in it that refer to time and a total energy. But since we're going to be interested in what happens close to singularities, what happens at infinity isn't going to bother us too much. So what are some of the properties of this thing? We're really interested in what's called superspace. That's the space of all 3 geometries. That's the same thing as all 3 metrics modulo diffeomorphisms. So it's really superspace that we're interested in. Classical solutions to Einstein's equations are going to be curves in superspace, and the curve simply represents how the thing evolves in time. Each point in superspace corresponds to a 3 geometry. So this curve sweeps out a collection of 3 geometries as you see it in space-time. But of course, if we go back to these diffeomorphism constraint equations and the Hamiltonian constraint, they do not have time anywhere in them. And so time has sort of disappeared in the canonical formulation, and this has led to a great deal of confusion over the years, almost half a century since it was discovered. The basic point is that time does not really show up in superspace. Superspace has singularities in it, and it's very easy to see that. The negative direction corresponds to conformal factors, and if the conformal factor sends the determinant of the metric to 0, that corresponds to a singularity. But a singularity in superspace could be one of 3 things. It could signal topology change, it could signal just bad coordinates, or it could be an honest space-time curvature singularity. all of the singularities in superspace come from the conformal factor doing something strange, because orthogonal to that, if you fix the conformal factor, then what is left is just the symmetric space SL3R over SO3. So that's the basic arena in which all of general relativity takes place. Lastly, of course, studying all of superspace is rather complicated. A truncation of superspace is referred to as a mini superspace. And again, a point in mini superspace corresponds to a 3 geometry, and solutions of the Einstein equations correspond to curves in this 3 geometry. Now, we don't want to do classical physics because we know what happens in classical physics. You make a singularity somewhere inside the black hole, and that is catastrophic. We want to look at what happens in quantum mechanics. In quantum mechanics, you can easily quantize the system. You fix the gauge to whatever you like. A popular gauge to fix is alpha equals 1, beta equals 0. That's not quite what we're going to do here, but you can fix any gauge you like. The momentum will be replaced by minus I times the functional derivative of gamma with respect to gamma at some particular point, and we'll introduce a wave function, psi, which is going to take its arguments in space of all 3 geometries, in superspace. We know that it takes place in superspace because if we look at the constraints, we want to regard constraints as projections on the form of psi. Chi I of psi, the diffeomorphism constraint, tells you that you want your psi to be independent of the geometries, so independent of the independent of the coordinates you've picked on superspace. Basically tells you that the diffeomorphism isn't going to do anything. And you're left with H acting on psi, a sort of analog of the Schrödinger equation, usually called the Wheeler-DeWitt equation. And these 2 equations, that once you've picked the gauge for alpha and beta, is all that's left of the Einstein equations. Another way of looking at this is to define your psi as a path integral. You can say that psi is given by the integral over all 4 metrics that have the geometry gamma as a single boundary. So you could regard this as another way of finding solutions to the Wheeler-DeWitt equation. If we go back to this, another way in which you can think about this psi, and I didn't write this out, but it's something that was first shown by DeWitt and by Ulrich Gerlach, again back in the 60s. If you write psi in the form some kind of amplitude times e to the I w, which is essentially the WKB approximation, I should say e to the I w over h bar, and take the limit as h bar goes to 0, and again you have to put an h bar in here, then you can show that in the WKB approximation, you end up back with the Einstein equations. So this really is a way of looking at the Einstein equations. So we have found a way of looking at the wave function. It's the probability amplitude for some 3 geometry 3G. I'm going to take it that that's the correct interpretation of this Wheeler-DeWitt wave function. Now let's go back to looking at gravitational collapse. Realistic gravitational collapse is not spherically symmetric. So the Oppenheimer picture isn't something that you want to really look at. But fortunately, Belinsky, Kalatnikov, and Lifshitz, E.M. Lifshitz, not his brother I.M. Lifshitz, showed that classically, as one approaches a space-time singularity that is space-like, the behavior becomes chaotic. Space becomes split up into separate domains, and these separate domains behave more or less independently. Let's concentrate on one particular domain for the moment. what happens is that classically, the metric looks like the Käsner universe. That is to say, there is going to be expansion or contraction along the x-axis, along the y-axis, along the z-axis. And as t goes to t0 from below, this thing is going to become singular. In the Käsner space-time, we're all used to the idea that p1 plus p2 plus p3 is equal to 1, and p1 squared plus p2 squared plus p3 squared is equal to 1. This equal sign should be a plus. And so what that is telling you is that as you approach the singularity, if the singularity is in the future, two directions are contracting and one direction is expanding. Well, that was nice enough, but it's not quite right. Whilst this is an example of mini superspace, it's not exactly what you get as you approach the singularity. As you approach singularity, you'll discover that the Käsner evolution in a particular domain is divided up into epochs. And in the transition between the different epochs, two things can happen. The first is that the parameters pi will change discontinuously, and the principal directions also change in a discontinuous fashion. So if you go back to this thing, these p's change from time to time, and the direction of the x's, y's, and z's undergo a rotation about some particular axis, the details of which I'm not going to try to describe. But there is these discontinuous changes. However, there is a nice way of describing what these discontinuous changes are in a slightly different way. If we look at space, the geometry of space at any point in time is just flat. So we can look at flat space in a slightly different way. Here is a metric on flat space, minus d rho squared plus rho squared over v squared du squared plus dv squared. Du squared plus dv squared over v squared you can think of as being just hyperbolic space. It's a Lobachevsky plane. If you ask yourselves about where this thing is singular, it's at rho is equal to infinity. And the way in which you can think of the evolution of Belinsky, Kalatnikov, and Lifshitz is as a null geodesic in this space. Now, if you want to describe precisely how that works, it turns out that it's not all of Lobachevsky space, but a particular region, which I'll call F, in the UV plane. You can project this null geodesic into the UV plane, and you'll discover that the way in which it behaves is according to this black line. So here is a straight line. This is a geodesic, a null geodesic but projected into UV space. And it's constrained to lie in this region here, which is bounded by, well, in the UV plane, V has got to be bigger than, well, lie outside the unit circle in the UV plane. U is bounded by 0 here and 1 here, and the unit circle here. And the motion is, well, Käsner motion is along a straight black line like this, but where the p's and the axes change discontinuously, it corresponds to a bounce off the wall here. So the BKL evolution corresponds to bouncing around like this, somewhere inside this region F. If you look at this, you will say, I have seen this picture before. And you will say, this looks like half of the fundamental region of SL2Z. And indeed, it is exactly half of the fundamental region of SL2Z. It is in fact the fundamental region of GL2Z. And the basic difference between the two is that SL2Z doesn't mix up holomorphic and anti-holomorphic bits, but GL2Z does. So F is the fundamental domain of the group GL2Z. Each QGASLAB epoch is associated with an element of GL2Z, and each bounce is represented by an element of the Weil group of GL2Z, which is A1++. That is to say, it's some Kac-Moody group that is hyperbolic. If you were skeptical about these ideas, then the work of Pretorius and his co-workers seems to support this kind of behavior inside a black hole. But that's classical. We want to do quantum mechanics. So let's look at the quantum mechanical version of this. Well, the diffeomorphism constraint isn't going to be interesting because we've fixed the geometry to be just one member of this, at each instant of time, one bit of this QGASLAB universe. You're just left with the Wheeler-DeWitt equation, which, when expressed in mini-superspace, looks a bit like some kind of wave equation with which we ought to be familiar. So it's minus d rho squared plus b squared over rho squared d2u squared plus d2 by dv squared. So this bit here looks like what you'd expect from a Laplacian on hyperbolic space. It's not all of hyperbolic space, it's this region F, and you're going to have to specify some boundary conditions on the wave function on the walls of F. What do you have on the walls of F? Well, classically you bounce off the walls, so that tells you that psi is equal to 0 on the walls of F. That's rather nice because that tells you that the solutions of these equations are given by the eigenfunctions of this thing here in the fundamental region F. But you know what those are. Those are basically just the odd mass functions of SL2Z. So this is related to some interesting number theory problems. As far as the eigenfunctions here are concerned, but those are going to dictate the behavior as functions of rho. And what you discover is that mod psi always falls off as rho to the minus a half as rho goes to infinity. Now that's interesting because it's telling you that the wave function vanishes as rho goes to infinity. Rho going to infinity is where the singularity is. So that's telling you that the wave function, the amplitude for finding that particular geometry, is going to 0 as you approach classically what you think of as the singularity. Now, of course, there's no reason to believe that the geometry in gravitational collapse is significantly different from what you see classically until you get into the quantum regime. And so the picture that we originally drew seems to be fine until you get close to where you thought the singularity was, where you discover that the wave function is going to 0. That's a boundary condition in the future. So what it would seem to be logical to do would be to say that means that the final state density matrix close to the singularity had better be 0. Otherwise, it would be inconsistent with the idea that the wave function vanishes there. That doesn't affect what happens outside the black hole. You can put the density matrix equal to the unit matrix outside the black hole. So you're just simply imposing a final state density matrix condition for the black hole, which tells you that at the singularity, everything has disappeared. in effect, what you're saying is that causality in its usual form does not hold inside the black hole. And that means that strong subadditivity of entropy does not hold either. So in that sense, you solved problems 1 and 2 that we started our discussion with. Now, of course, there's some other problems with this. The first is that this does not explain how information can escape from inside the horizon and find its way outside, because we're saying that at least unless you're close to the singularity, classical physics ought to be, or semi-classical physics ought to hold. How could that possibly happen? Well, the one good thing about the treatment of Aharonov, Leibowitz, and Bergman is that the two legs of the path integral are not independent of each other. That means that there are at least Euclidean wormholes that would appear in such configurations, but whether they actually solve the problem or cause something terrible to happen, I do not know. So one wants to ask, are there going to be any tests of these ideas? I don't know. The question is whether or not anything interesting happens outside the horizon that you could use to test these ideas. I don't know. Hopefully it doesn't cause anything terribly bad to happen outside the horizon. And the challenge now is to see whether or not, well, how information is lost and whether it really gives a realistic explanation of how black hole evaporation takes place. I think that's a convenient place to stop. The basic idea is that you have to impose boundary conditions in the future, but that seems to be natural, at least if you think of physics in the way in which it was done in the past, according to Aharonov and his friends. So I think, as I say, that's a good place to stop, and we can look for questions.
Oh, sorry. Any questions?
That sounded a bit like a protest.
It is a little bit like a protest. To be fair, she woke up halfway through your talk and sat through the rest of it quite happily.
Ah, splendid. So she can work on this problem.
I'm sure at some point she will. Any questions, anyone? I strongly encourage the students, if you have any questions, Malcolm is the expert in this topic. You really want to...
Actually, I'll ask a question because there was something which I said I was going to say something about and didn't. Everyone is upset, or at least has been upset at some point in their lives, about the fact that gravitation is an unrenormalizable theory. So I should explain, do not understand why this has ever been regarded as a problem. So here is the reason. You see, if you ask yourself about renormalizability, you're basically asking about the ultraviolet behavior of the theory. And the ultraviolet behavior of the theory in gravitation is very bad. And you know it's very bad if you treat it in perturbation theory. Let's contemplate what happens if you start off with a massive particle, say, with very small mass. Its quantum wavelength is enormous. Let's crank up the mass. The quantum wavelength goes down and down. That says that high energies correspond to shorter distances. But let's ask ourselves what happens if you crank up the mass so far that the quantum wavelength becomes equal to the mass, roughly speaking. Then, if you believe in the Hooke conjecture, that tells you that you form a black hole. That cannot be described in perturbation theory. So if you ask yourself what happens when you try to think about high energies in a quantum field theory, well, you think about doing integrals over the momentum, for momentum, integral d4k. But you know that large k corresponds to something which ought to produce a black hole, and there's no way which you're going to describe that in perturbation theory. So the fact that you have lost the ability to renormalize something should come as no surprise. Perturbation theory doesn't work. Why are we so surprised by this? Well, I'm not. Does that tell you how to deal with the problem? No, unfortunately.
So, okay, so that's a really interesting point. I mean, I guess I am also not surprised by it, but perhaps for a slightly different reason, which is that you know, in let's say for Fermi theory, it's not renormalizable, but we understand that it's not a fundamental theory; it's an effective theory. And so, if you regard gravity, I guess, as an effective theory, to be corrected once we know how to treat the parts of it that break down when you crank up the K.
Right.
And your point, I guess, is that one of those things is the emergence of black holes, which we don't know how to deal with perturbatively. In the same way that I guess you could look for, I guess, solitons or other non-perturbative degree of freedom in just straight up non-renormalizable field theories, right?
Sure. Yeah. Mm-hmm.
Yeah. All right. Yeah, it's an interesting viewpoint. Yeah. Any other questions? So Malcolm, I guess one question I have is more big picture, which is, where do you see this program going? Is where to from here?
So that's a good question. It seems to me that there are there are at least two things which seem to me to be something which I'm looking at. The first is that I want to see how the information actually escapes from the black hole. This simply tells you that there is a mechanism by which information may not escape, but it doesn't tell you how. So, as I was hinting at, since the forward and the backward legs of the path integral interfere with each other, the question is, does that enable you to allow the information to escape? Of course, there are various people who tell you that Hawking radiation is in fact tunneling out from stuff inside the horizon to outside. Harrier and Wilczek being the obvious candidates for such an explanation. But that's at a sort of very semi-classical level. Here, you already know that there are Euclidean wormholes which could show up in the path integral. They were discussed in this context by Hawking back in the 1980s. But they are Euclidean, and so what you really need to do is to see whether or not the kind of treatment that you require in Picard-Fuchs approach to path integrals allows these field configurations to contribute, and if they do, whether they contribute too much or too little. And in actual fact, that's something that you ought to do independently of whether or not you think that a final state boundary condition is something that you want. The second thing which comes out of this really coincides with some of the ideas of Hermann Nicolai and Thibaut Damour and Mark Henno, and that is that it might well be that the fundamental degrees of freedom of the gravitational field are described by, at least in the case of pure gravity, the Kac-Moody group A1++. You can add various matter fields into that picture, and unless you add in master scalar fields, you still always seem to end up with various hyperbolic Kac-Moody groups. And perhaps it is that those things are fundamental rather than geometry of space-time. Even if you didn't think that, you should be a bit suspicious, because in this picture, time is emergent. And in a certain sense, geometry is emergent too. That's because if you look at the WKB approximation, writing the wave function e to the IW, and take h bar going small, then what you discover is that time emerges. And so you might think that somehow in this kind of picture, then it ought to be space emerges too. It's true that you've done something, because you've done something canonical, you've singled out time as being different. But indeed, time emerges. It's not a fundamental thing. So there's a hint that that's the right way to go. So those are two of the things. One extra possibility is asking if there are any tests of these ideas. I think this doesn't work, but I also think that someone at Perimeter thinks that it does. So if you thought this picture was the right picture, you might start to wonder whether or not there would be echoes in gravitational waves signals from black hole collisions. I don't think there are, but as I said, someone does think that there might be, so that would be interesting too.
Right. Any other questions?
Well, I have one other observation then. This does not solve the information paradox. It merely points the way in which you might try to do it.
Well, that's good. I mean, it's always nice to know. You know, I remember when we were setting up the panel discussion in strings last year, and you were moderating it. You know, prior to that, there was lots of talk by a number of very prominent string theorists who thought that, you know, this would be great because we're going to announce the solution of the information loss paradox. And I think the one takeaway that I had from that panel discussion was that it is very, very far from solved.
Very far from solved.
Yeah.
In fact, I don't understand it. You see, whilst it's true that JT gravity and islands and all of that tell you something about what's going on. Let's look at the islands situation. I mean, the islands tell you what is entangled with what has got to be entangled with what and where it is, but it doesn't tell you how information is not lost.
Yeah, that's quite true. Yeah, I mean, you know, but and that said, I guess the biggest point in opposition would be from Samir Mathur and the fuzzball picture, right? I mean, he was completely contesting the whole JT gravity solves the problem story.
Well, it's right. I don't terribly like fuzzballs myself because it seems to me that that's basically saying that physics close to the horizon, well, physics close to the horizon is not described by Einstein gravity, whereas black holes and the problems that, well, you know as well as I do. You've got to question is whether or not there are modifications to gravity that support the fuzzball hypothesis that don't get you into some other kind of trouble. And so I don't know the answer to
that. Yeah, that's true. There was something else I wanted to ask. So a couple of years ago, I heard Aharonov speaking at Princeton. And,
yeah.
And he was talking about specifically this idea of post-selection in a quantum system and how this leads on to the idea of weak measurements. So in the post-selection story, you specify, well, I guess I'll phrase it in the language you use. So you specify an initial density matrix and a final density matrix. And then there's some measurement that you can do in between, right? And I guess this would be a weak quantum measurement in the.
Yes, but you probably have to do that inside the black hole.
Okay, so that was my question: is where would you have to make this measurement in? Okay, right. I see.
So that's not one thing I would want to do.
But then could you, in the JT gravity situation where you're studying at, ADS2, which is, the whole thing behaves like a black hole.
Right.
Could you make the measurement there?
I don't know. I guess that's something that one could look at. I haven't tried.
Okay, yeah, that's interesting.
Cool. I encourage you to try.
Yeah, I must say the information loss paradox is something I've only taken a bystander approach to. I mean, there are various,
Oh, but you do have tenure, so you're allowed to do it.
That's true. That is quite true. I'm using it for other nefarious purposes, like quantum batteries and other exotic things.
Suppose that you thought that it all worked in JT gravity. I mean, it wouldn't make any sense to me. It's like saying, well, just because it works in 2 dimensions doesn't mean it's going to work in 4, for the very simple reason that gravity in dimension 2 and 3 is a very strange thing.
Mm-hmm.
So
that's right.
I was encouraged a long time ago to ignore anything that ever happened in dimensions 2 and 3 if I was talking about something gravitational.
So was I, actually. George Ellis was one of my co-advisors, and I think the Dennis Sharma school was very clear that in D less than 4, gravity is trivial, and you ought not to think about it.
Exactly, and the person I was thinking of was Stephen.
Right, exactly. They're
not
from the
independent.
same school, right? Yeah. So, but I did learn one thing. Well, I learned lots of things from your talk, but one thing in particular that I'm going to take back to George, which one of the things he keeps raising, and it's an entirely obvious thing when you think about it in hindsight, but I've never raised this point with him, is that he always talks about how the universe, how could you have a wave function for the universe? There's, what does it mean to have a wave function for the universe? But you put it in a very nice way.
But it isn't a wave function in the universe. It's a wave function. It's a wave function. It's an amplitude for A3 geometry.
Exactly. In superspace.
On other things.
That's right. And so that's the way to think about it. Yeah. Yes. That's yeah. Thank you. That gives me some ammunition for the next argument we have. Very good. Any other questions for Malcolm? If not, I want to thank Malcolm very, very much. It's been an absolute pleasure to hear you speak. And as soon as our country's clear red lists.
Oh, you are off the red list here.
Yeah, that's true.
But I'm not sure we're off your red list.
I think we're very happy to take your pounds. We have no moral compunctions against. But as soon as you want to travel here, you have an open invitation. We would love to have you.
I would love to, and I'd much rather have done this on the blackboard.
Good. Great. Well, thanks so much for speaking, Malcolm. It was wonderful to see you again.
Thank you very much for the invitation. And say hello to George.
I will.
Fantastic.
Take care.
Bye.
Thanks, everybody. Bye-bye.
Thank you. Bye.